Okay, let's continue our session. Let's start the last talk before party. So today's last speaker is Igor Makhlin from Beijing University, who played very important but invisible role in the organization of this conference, and he will talk about governing polytopes in Lie theory.
Thank you, Zhenya, and thank you to the organizers for inviting me. It's a great conference we're having here. Yeah. I work in TU Berlin. That minor correction.
So sorry, I usually mix up Berlin and Beijing.
No problem. Oh yeah, we should probably turn on the light here. Well, is there another? Well, I mean, I don't know. Okay, yeah, that's great. Thanks. Okay, let me start. So, well, here you can see the title of the talk. So I'll just start with a disclaimer that, well, governing polytopes is not a term. This is just well, an adjective or a participle I'm using to describe the fact that certain polytopes, I'll be more specific in a minute, but certain polytopes govern or maybe provide, although provide is not quite precise, a variety of structures in Lie theory and algebraic geometry which are described through the combinatorics. So more specifically, but still kind of vague, here's the situation we're going to deal with. So let's consider lambda I'll write a bit smaller than that if that's okay, an integral dominant weight of some, say, simple Lie algebra G, and then, well, there are situations, somewhat typical situations, when with such a weight we associate a polytope, right? This is a polytope, I mean, for now, just some kind of polytope, which defines several of the following structures. So maybe first of all, it provides a toric degeneration of the flag variety associated with this weight. So the flag variety is G. This is the group modulo the parabolic subgroup which stabilizes the highest vector. Each highest weight defines some kind of parabolic subgroup. So by toric degeneration, again, I will give some details on that, but the meaning is that the toric variety of this polytope can be realized as a flat degeneration of this flag variety. Okay, so one thing is toric degenerations. Another thing is basis. So lattice points in our polytope enumerate a basis in V lambda. V lambda is the corresponding irreducible representation. Well, I mean, this is imprecise, of course, because well, if you have the right amount of lattice points, you can always enumerate a basis with them. So, and in practice, there are many different ways of attaching basis vectors to lattice points, but for now, let's keep it this way. And so maybe a third thing is standard monomial theories. This is okay. This is a monomial basis in the Polytopes algebra. And by Polytopes algebra, I mean the coordinate ring of our flag variety, right? So, I mean, well, okay, so, well, first of all, this is similar to, for instance, the famous basis in the coordinate ring of the flag variety, which is enumerated by semi-standard tableaus. I'm sure you've seen this construction. Well, many of you have. And so in principle, so this is, well, we will see examples later on. And well, here the arrow, I mean, let me draw the arrow this way because this, well, it's not quite true that this is uniquely recovered from polytope. Maybe in some way, in some sense, it's the other way around. The polytope is recovered from the basis, but whatever. And then there are others, right? So there are other things like you can have a Newton-Okounkov body. Of, again, the flag variety, which is associated with the line bundle. There's an equivariant line bundle on the flag variety corresponding to our weight. And, well, with it, you can associate something known as the Newton-Okounkov body, which is, well, some kind of convex body. And it often, this same polytope can be realized in this fashion. I'm actually, so these three structures I'm going to talk about in more detail. This I'm going to omit. So, but this is another example of a structure which comes from a polytope. And I mean, there's other stuff, right? I mean, you can, they can define something known as degenerate representation theories, or, well, not really known as, but I'd call them this way. And then, for instance, if you have a toric degeneration, you have a corresponding, you have several combinatorial structures coming from it, a maximal cone in the tropical flag variety. You have a matroid subdivision, which, well, I mean, other structures, but I will concentrate today mostly on these three. Okay, so the main point is that there is, well, a fair amount of work which construct or discuss polytopes which provide at least two, or maybe sometimes even all four of these kinds of structures. So maybe let me briefly mention some examples in the literature. So maybe the most famous family are the string polytopes, right? So this is due to, well, maybe Bernstein Bernstein-Zelevinsky, and later on due to Peter Littelmann. And yeah, so I mean, I'm obviously not going to define those, but there are certain polytopes associated with highest weights. And so there's a series of papers which, for instance, there's a paper by Caldero where he constructs the toric degenerations corresponding to these polytopes. Then there are works by Cave, by Q-Mars Cave, who constructs the Newton-Okounkov bodies corresponding to these polytopes. And okay, so I mean, in the original papers, the authors construct. I'll mention this in a moment. In the original papers, the authors construct canonical basis in the quantum algebra associated with these polytopes or cones over these polytopes. So this can be sort of considered as an example of this. Okay, so I mean the standard monomial theories, I don't think they really exist in these generalities, but I'm pretty sure that's possible. Okay, so this is a very large family. There's also something known as essential polytopes. They, I mean, this term is applied to actually maybe two families. So there's the work of Zhenya Feigin, Ghislain Fourier, and Peter Littelmann again. Which construct certain polytopes in the context of essential monomials. Yeah, I'm writing a little small here. This is not very important. I'm just giving examples. But if this is completely illegible, please let me know. And I'm trying to really want to squeeze this part into one board. So I'm going a little small here. And then there's another paper by nearly the same authors, but where Zhenya Feigin is replaced with Xinfeng. And this is the context of birational sequences. And so the authors, they prove, once again, that the polytopes they obtain provide this, the basis, the toric degeneration, and the Newton-Okounkov body in both contexts. So these are two families of polytopes. Yeah, but the issue is that, so the construction, the definition of the polytope, it depends on some kind of datum. So here, this is some kind of adapted decomposition of the longest Weyl group element. Here, this is some kind of ordering of PBW monomials. Here, this is some kind of decomposition or ordering of the positive roots. And these structures, whatever they are, they should satisfy certain nice properties. And the problem is that there's no clear recipe for constructing examples with these properties. So we know certain examples, we know that they satisfy these properties, but we do not have good recipes to construct large explicit families. This is sort of an issue which has been bothering me. And yeah, so we are gonna discuss one such family today, which is very explicit and, well, fairly large. So this was an intentionally vague introduction about what I'm gonna do. And I will now concentrate on, well, for the next part of the talk, I'm going to concentrate on two very explicit examples of such polytopes, but before I do that, let me maybe recall some basic notions. So from Lie theory, so maybe concerning, first of all, the Plücker. So I'm going to concentrate on type A for now, so SLN. Type A. So maybe let me first recall some details concerning the Plücker embedding. Plücker embedding of well, the complete flag variety, which I will denote Fn, right? So this is the variety of complete flags in n-dimensional complex space, right? And we know, well, the Plücker embedding realizes this is a subvariety in a product of projective spaces, right? So multi-projective realization, where this is n-dimensional, then the next product is and choose two-dimensional, and so on until, well, the next product is again n-dimensional, right? So here we have the binomial coefficients from n choose 1 to n choose n-1 products. And, well, it is kind of obvious from the notion of a flag that the flag variety lives in this product. And in particular, this means that we have well, we can consider the coordinate ring of this product, the multi-projective coordinate ring, right? So this is the ring S, which is the ring of polynomials and variables x. Well, they're labeled by tuples of integers. Here, where I'll say that, so it's a strictly increasing tuple of integers between 1 and n, and k is between 1 and n-1, right? And we have an ideal I in this ring, which cuts out this variety in this product. And so this is the Plücker ideal. Well, I guess this is more or less all I'm going to say about the Plücker embedding. Well, now maybe the next thing is some basic notation concerning SLN and its representation theory, right? So I'll denote the positive roots by alpha ij, right? And where this is a pair of integers between 1 and n. The first is smaller than the second, and well, here I mean that alpha ij is simply the sum of the simple roots from the ith one to the j minus first one, right? So I mean, occasionally people denote this by ij minus 1, then this inequality is non-strict, and we have n minus 1 here, but I like this convention. So these are our positive roots, right? And then for every such pair, for every positive root, we have the corresponding negative root vector, right? So this is an element of the algebra. I mean, and the important thing is that it's the negative one, right? The ones which act non-trivially on a highest weight. I'll get to that in a second, but maybe before I do that, so maybe let me denote the set of all such tuples by p plus, because it kind of enumerates the positive roots. And then I'm going to use the following notation. So consider a point, just some point x, in with integer non-negative coordinates enumerated by our set p plus, right? So for every such pair, we've chosen a non-negative integer, and then we can consider this. So this will denote the PBW monomial. So this is a product of Fij to the power Xij, right? And this is a PBW monomial, right? So it lives in the universal enveloping algebra of SLN. And great. The only thing I have to specify is the order of the factors here, right? Because, I mean, in principle, this is, they do not commute. So this is ordered, well, ordered, I'll just say first by I, and then by J, right? So this means that we order, so these factors, these Fij's, they're ordered, I increases from left to right, and within a fixed I, J increases. This is not very important. We can consider other orders, and in fact, we could actually order first by J and then by I, and that would be literally the same monomial if you think about the commutation relations, but whatever. I'll just choose this one. And finally, maybe, so one more piece of notation concerning this is that, so we have, let omega 1, omega n minus 1 denote the fundamental weights, right? And then if we have a weight lambda, so this is just some linear combination of these fundamental weights, then, so I'm going to consider its coordinates in a different basis. So I'm going to write, this is somewhat standard, right? So I'm going to write that lambda 1 is the sum of all the alphas. And then lambda 2 is the sum of all the alphas starting with the second, with alpha 2, and so on. And lambda n minus 1 is alpha n minus 1, and lambda n is 0. So I'm going to use this notation. And so you can see that if lambda is dominant, that means that these alphas are non-negative, then this is just a non-increasing sequence of real numbers. Okay, so this is the notation, and maybe one last preliminary thing is initial degenerations. So consider any polynomial ring in some variables x1, xn. This is not very important. And consider so we will consider maybe, well, we'll consider monomial orders. Monomial order on, let's note this by R. On R is a order on monomials. Sorry. Where was the wipe that we had? So this is a partial order. A partial order, let's just denote it like this on all monomials, which is such that, well, one, it is multiplicative, meaning that if we have 3 monomials, say M1 and then M2, which is less than or equal to M3, then M1, M2 is necessarily less than or equal to M1, M3. So we can just multiply monomials by, we can multiply inequalities but by a monomial, and 2, the order is weak. So this is all very technical. We're not going to use this, so I'll just write that it is weak. This is a term in order theory. It means that incomparability is an equivalence relation. So in fact, the order breaks down to several classes of pairwise incomparable elements, such that the inequality is just determined by which 2 classes contain the 2 elements, whatever. And then if we have this, then we can consider, if we have such an order, then we can choose a polynomial in here and consider its initial part, right? So the initial part of our polynomial with respect to the monomial order is the sum of, or maybe let's just, sum of monomials in P, which are maximal with respect to our chosen order, right? So P is a sum of monomials. We pick, or terms, and we choose those terms which are maximal among all the occurring ones, and we only keep those. We throw the rest out. We get what is known as the initial part. Now let us consider an ideal J in here. Then we have an initial ideal, which is the ideal generated by initial parts of elements of J, right? So I mean, we choose all elements of J and we consider their initial parts, and we generate another ideal with it, but actually you can easily check that it suffices to consider linear combinations of such initial parts. They will already form an ideal. So this is an initial ideal. And I mean, the whole point of me giving this definition is the following fact. I'll use the second half for something else. So let me write a fact here. Fact. The fact is that the quotient, or maybe let me write it this way, the spectrum of the of R quotiented or factored out by the initial ideal is a flat degeneration of the thing we started, right, with. So we can take this quotient. I'm gonna need another chalk. Okay, here's one. Right, so I mean, we can associate a variety or a scheme with the idea we started with. We have another scheme for the initial ideal, and this is actually the generation of this again, so I'm not going to go into the details, but this means that there is a flat family, a one-parameter flat family where the generic fiber is this thing, and then there's one point, actually 0, over which the fiber is this, right? So if you think about this flat family, you have this variety which is the same everywhere, but in this one place it degenerates into this thing here. I mean, these types of degenerations are interesting from many points of view. So this is usually simpler, but preserves many properties of this thing. So this is the slogan which advertises flat degenerations. And so here I wrote spectrum. I'm sort of considering an affine scheme, but of course, what I'm going to do, you can, I mean, if the ideal is homogeneous or multi-homogeneous, you can replace this with proj or multi-proj, and actually I'm going to need multi-proj, but it all kind of works the same way. Okay, so that's that. Are there any questions concerning this, these preliminaries? Well, if not, then let me cut to the explicit examples. So maybe there are going to be two of them, the Gelfand-Tseltin polytopes and the FFLV polytopes. So I'm going to associate these kind of structures with them. And maybe a disclaimer number 2 is that, so these are kind of known results, which have been known for a while, but the way I'm going to explain them is rather non-standard. It is tuned towards the generalization, which I hope to explain in the end. Okay, so Gelfand-Tseltin polytopes. What is a Gelfand-Tseltin polytope? So we choose lambda, right? We choose a integral dominant weight lambda, and we have its coordinates in this form which I defined, right? And so this is, we will define a polytope Q of lambda, which lives, well, it will live in the real space with coordinates enumerated by P. The issue is that I have not defined P yet. I've defined P plus. So there is a subtle difference here, right? So P is a slightly larger set. It consists of pairs ij, for which I and j now may be equal, right? So the only issues is that the only difference is that we've added pairs of the form II. So this has n more elements than P plus. Okay, so this is a polytope which lives in this real space, and now you can see that the coordinates in the space, these pairs ij, they can be naturally written in a sort of triangle, right? So in the top row, we will have n elements. This will be the coordinates 1, 1, 2, 2, 3, 3. Then in the next row, we have, well, let me just let n equal to 4. And in the next row, we have coordinates x 1, 2, x2, 3, x3, 4. Then here we have coordinates x1, 3, x2, 4. And here we have x3, 4. So I hope this is more or less clear how we place the... Oh, sorry, yeah, thanks. This is x1, 4. And so we can write down a point x like this. So yeah, the only difference is that the top row was denoted like this because we are only going to consider points where these coordinates in the top row are the coordinates equal to the coordinates of our chosen integral dominant weight. Okay, and so, I mean, the definition of the polytope is now very simple. We just write, and so we have this triangle and we have sort of adjacent elements here, and we write that they satisfy all the inequalities sort of decreasing to the right? So I mean, I hope you get it. So obviously, this is then a convex polytope, which is bounded. It has finitely many lattice points and so on. So this is the classical definition, which goes back to the 50s, I want to say, and to Gelfand and Tseltin.
Lambdas are all different or not?
Not necessarily, no. So in a moment, we are now actually going to consider the case when they're not different at all. So what is Q of a fundamental weight, right? So how does this work? We have the fundamental weight is written down somehow like this, I guess, right? And maybe let's just let n equal 5 here, right? So this is omega 3, right? And then, so we have some elements in our triangle, but the main point is that due to our inequalities, all of these must be 1s, right? And all of these must be 0s. And then we have some elements here, which are, so there are 1s here. Okay, and let me, so for instance, let me write a, let me write a 1, what is there? Oh, okay, I see. Sorry, yeah, so this element is included. Let me write a 1 here, maybe a 1 here, a 1 here, and a 1 here, and the rest is 0. And so all of the lattice points, all the integer points in this polytope, they're of this form. I mean, in particular, you can easily check there's n choose k of them. And we will now define a map. So maybe let me first of all define the set of these lattice points by pk. So these are the lattice points in omega k, right? All the points with integer coordinates. And then now I'm going to define a map phi from pk to to k tuples in 1n. Right? So I'm not going to define this very formally. The formal definition will be given for the general case, but the idea is that we consider so we can extend this to length n, sort of these skew rows, right? We can add a bunch of points here, so that each one of these rows now has length n, and the elements of this tuple will be, so these guys here, so the length of these complementing columns, right? So for instance, here k is equal to 3. Yeah, so and this goes to 1, 3, 4, right? Because, well, okay, yeah, we'll have to add another row here. So this is 1 element here, 3 elements here, and 4 elements here. This is a little hand wavy, but I hope you get the idea. So this is our map phi. And the point is that the map phi lets us now very easily, this is the main thing, the map phi. So it lets us define all of these structures quite easily. So maybe let me first of all mention that phi, well, it sort of specializes to a bijection from subsets, or from the union of all the lattice point sets to subsets of the numbers from 1 to n. And so this is very easy to check here. And this sort of, what does this mean? So for instance, consider, or yeah, sorry, I was instructed to use the boards from left to right. So I should probably write here. So theorem. Consider the map. I'll denote it phi. Or we already have phi, so this will be psi. It will be a map from a polynomial ring in variables x, p, where p is 1, so where p lives in this set of lattice points, right? To the ring S, which contained our Plucker ideal, right? And psi maps xp to x psi of p, right? So this is a tuple of integers. So this is a variable in our Plucker ring. I mean, this tuple may not be increasing, but there is a standard convention that we can reorder it and multiply by the sign of the permutation. And so the theorem claims that psi of j, I will define j in a moment, is an initial ideal of I, right? So J is the toric ideal of our of Q of lambda for regular lambda, right? So you can easily check that if lambda is regular, then all of the polytopes are strongly combinatorially equivalent, which means they all have the same toric variety. And now, and then it is natural that to consider the toric ideal of this polytope in this ring, right? So in the ring where the variables are enumerated by these lattice point sets. And this means that the toric variety of Q of lambda is a, flat degeneration of the flag variety, right? So, and so this is one theorem, and well, I mean, in very different terms, this you asked about Ganchuolea Lakshmi Bai. So this is the result of Ganchuolea Lakshmi Bai from the 90s. So that this thing is a flat degeneration, as a toric degeneration of the flag variety. Of course, they did not notice that this is actually the Gelfand-Tseltin polytope. This was noticed later by Coggan and Miller. but whatever. So this is one theorem, and so I have how much time? Zhenya? How much time do I have? 5 minutes. Okay, so that's not a lot. I will only very briefly mention the generalization. Okay, so this is I will just have to restrict my attention to one of these structures, the toric degeneration. And now, so the main point here is that we have this polytope, and then we define this bijection from lattice points and fundamental polytopes to integer tuples. And using this bijection, we define the initial degeneration. So this goes a long way. This is sort of the point. Namely, we can generalize this approach to a very large, well, wide family of polytopes called the marked, a bit of a long name, marked chain order polytopes, right? So these are an example of poset polytopes, right? So we can view P as a poset with the order I1, J1 is less than or equal to I2, J2. And if and only if I1 is less than, no greater than I2 and J1 is no greater than J2. And we can then associate, and if we choose now a subset of P, we can define a polytope for every integral dominant weight associated with this set O. I guess I'll have to skip the definition, but so I mean we consider J a lower set in P, so a lower set is a subset of a poset which is closed under taking smaller elements, and from this we get a subset MOJ in our poset. So for every we choose a lower set, we from this lower set we get a different subset of P in a way which I'm not going to define, but now let me denote A, the set of all, so the set of elements of our poset which, so the top row in the diagram, and then we say that the fundamental polytope associated with weight omega k is the convex hull of the indicator vectors of MOJ, right? So this is just a point in RP, again, the indicator vector of this subset over all J such that their intersection with A has size K, so which contain precisely the first K of these elements. So, and this is a convex hull definition. It contains, it describes the lattice points, and it turns out that using this convex hull definition, we can associate, so the lattice points are enumerated by ideals. To construct a bijection, a map, similar to these, we need to associate a tuple with every J, right? And this is done via pipe dreams, right? So I don't have any time to define what this means properly, but MOJ is a subset in our poset, in our triangle, right? So it's a bunch of elements and a bunch of marked elements in this triangle. And I guess many of you, especially, I mean, there's some experts here on Schubert polynomials. You have seen how one may associate a permutation with this kind of subset, right? One draws this thing, which is called the pipe dream, and one gets, so from this subset M of P, one gets a permutation WM. Okay, and so this, I'm about to finish. This lets us define our map from lattice points to tuples, right? So one takes a lattice point. A lattice point here is, well, the lattice points are enumerated by lower sets. And so we need to take a lower set J and associate a tuple with it. And this tuple is, or this is simply the first K elements of the permutation, right? So we apply this, we take the permutation corresponding to the permutation corresponding to the subset corresponding to J. We apply it to the integers from 1 to, well, to this thing here. So K is the intersection of J with the top row, right? And we get a K tuple. And now, since we've associated a K tuple to every lower set, and thus to every lattice point in a fundamental polytope, we can actually write down a theorem. I would say it's similar to this one, but it's actually literally the same theorem in these notations, only there's a typo here, there should be fine, right? So we have the same exact map between the polynomial rings. And so again, this, if we go from tuples to subsets, this is a bijection. This means that this map is an isomorphism. And this isomorphism takes the toric ideal of the polytope to an initial ideal of the Plücker ideal. And this means that our polytope is actually a toric degeneration. And that's nice. So yeah, maybe I should note that this is actually, I should mention Naoki Fujita, who was the first to prove that these polytopes also provide toric degeneration in a completely different way, which uses Anderson's theorem, which goes from Newton-Okounkov bodies to toric degeneration. So his interest was in Newton-Okounkov bodies, who he defines geometrically. And this is sort of this alternative approach, which we extended to these other structures, we meaning I. And then Zhenya and I wrote another paper where we do this for types, Dynkin types C and B, which is kind of nice because Fujita was not able to cover type C. And then also this can be done in the semi-infinite case for semi-infinite Grassmannians. Okay, but I'm 5 minutes late, so I should stop.
Thank you.
Thank you.
So, questions?
So my question is that, do I understand right that this construction is kind of uniform construction for having like Gelfand, Tseltin, Bernstein-Levinsky, FFLV, and my other question is like, what else do you have in this zoo?
Right. So Right, yeah, so first of all, concerning FFLV, it does work for FFLV. I was going to give an explicit description of this. I quickly realized I will not have the time for this, so it works for FFLV, right? Because there we also have this natural correspondence between, it is also a poset polytopes. It is, maybe I should mention that, well, I didn't give the definition here, but if O is O of P, we get the Gelfand-Tseltin polytope. If O is empty, we get the FFLV polytope. Maybe, well, this can be considered the definition. But if we go to string polytopes, to Bernstein-Zelevinsky polytopes, well then, no, not really, because, so this is, of course, this is all very specific to this poset polytope structure, right? But this actually raises the question of how far can we take this? This is something that should be addressed. Because this is done for these marked chain order polytopes, but there is no real reason. There are more general families which have sort of a similar structure. Can we take this any further? Maybe we can somehow describe all string polytopes as poset polytopes.
Thank you.
I just want to ask you about another famous polytopes is flow polytopes. Are there relations of Gelfand-Tseltin polytopes and the flow polytopes?
All right, so the flow tope, who are they? So the question is whether the flow well, I mean, I can say right away that I don't know. But I think not. So you're asking if the flow polytopes are part of this construction, right? Yes, no, I mean, so yeah, as I was trying to say here, there are many families of polytopes which have these Lie-theoretic applications. And the problem is, so I don't remember the details concerning flow polytopes, but so my guess would be that once again the construction relies on some kind of structure which is assumed, some kind of combinatorial datum which is assumed to have nice properties, and there is no explicit recipe for constructing this datum. This is kind of the issue here. So in these families, we do not have good recipes for constructing elements of these families, the polytopes. Unlike this marked chain order polytope story where the polytopes are defined very explicitly. So I mean, here I've defined them for the fundamental weights, and for a general weight, you just take Minkowski sums of these with the corresponding coefficients, and you get a polytope for a general weight. So this is very, very explicit. You can choose any O, and you can write down the polytope, and it will always have the desired properties. This is kind of the advantage.
Okay, thank you. So if you have more questions, please ask Igor during the banquet.
No, that's the best thing to discuss during the banquet.
So let's ask the speaker again.